continuing with our applications of vectors as force. Let's look at this example. A large retail store hangs signs from the ceiling identifying different sections of the store. Each sign weighs 25 pounds and is suspended from two identical chains that make 30-degree angles with the ceiling. Find the force, the tension, in each chain. Okay, so let's think about what's happening here. So we have a ceiling, and then we have chains hanging down from that ceiling, and they hang the sign, right? So there's a force on that we need to figure out. Okay, so first off, we have the force due to gravity, right? The weight of the sign that's pulling it downward. And then we have 30-degree angles with the horizontal. So that means that this angle right here is 30 degrees, and this angle right here is 30 degrees. And then we also know that the chains are identical. Okay, so we know the chains are identical, and that means that whatever the force is on these two, we know that it's the same. So they have the same force because they're making identical chains with identical angles with the ceiling. Okay. If we want to think of it this way, we have a vector, the force holding it up, right? And then we have the force pulling it down. And of course, this is in equilibrium because it's not crashing to the ground. So if I call this vector T1 and this vector T2, I know that the force due to gravity plus those forces, T1 and T2, must be equal to my resultant force, which must be equal to 0, the 0 vector, because the sign's not crashing. It's obviously getting somewhere. Okay, so we know that's the case. We know the force due to gravity. Force due to gravity is actually pretty easy. I'm going to write the forces over here. Force due to gravity is 0, negative 25. Pretty easy, pretty straightforward, because it's pulling it down and only in the downward direction. Okay, so what about these other two vectors? Well, they're a little more complicated. So T1, that vector that's holding it up, would be equal to, now T is the magnitude of this vector, so it would be T times the cosine of the angle, and then T times the sine of the angle. Now the question is, what's the angle? Well, for this vector, if you imagine, here's the top of the sign, right here. That's the positive x-axis. We're basically placing the origin right there. Right? So that's the origin, because it's convenient to put it there. Okay, so that angle 30 degrees is the same as this angle 30 degrees. And so that's going to work out. That'll be our angle. So this force vector here has a 30-degree angle, no problem. So we're going to put 30 degrees and 30 degrees. Okay, we can find those values. Matter of fact, we know what those values are because we've passed pre-calculus. So this is the square root of 3 over 2. And this is a half. So this is square root of 3 over 2 times t and a half times t. Okay, now what about T2? Okay, T2 is the same thing. It's going to be T cosine of an angle, T sine of an angle. But the angle is a little bit different because it's 30 degrees up here. So if you think of the horizontal, let me think of a color here I can use. Here, I'm going to use this green pen here. So this angle here is 30 degrees, but that's not the angle with the positive x-axis. The angle with the positive x-axis is all the way over, from here all the way over to here. And that would be 150 degrees. So that would be the angle that we would put in here. I didn't like my color choice, so I made it lightly blue. Okay, So I know that if I add these up, oh, and this we know. Again, 150 degrees is on our unit circle. So we know this is negative square root of 3 over 2t, and this is a half t. Those values are known. Okay, so now I can just plug in all the pieces I know and set it equal to 0. And I can solve for t, which is what I'm actually looking for, the tension in the chain, the magnitude of that force. Okay, so 0, negative 25, plus, and then the square root of 3 over 2t, 1/2 t, plus the negative square root of 3 over 2, and then 1/2 t. And it has to be equal to the 0 vector. So each component has to be equal to 0. So think what the 0 vector is. It means that, and let me just kind of segment that off because that's side work. 0 plus the square root of 3 over 2 minus the square root of 3 over 2 has to be equal to 0. Here, actually, let me write the 0 vector just so you guys can see it. I think I can fit it in there real quick. The 0 vector is 0, 0. That's a 0. Okay, so 0 plus the square root of 3 minus the square root of 3 has to be equal to 0. Oops, that's t, which is fine because that's 0 equals 0. No problem. That didn't help us. That didn't solve us for t. So it's the other one that's going to help us. We have 1/2 t plus another 1/2 t, take away 25, has to be equal to 0. So that's 1/2 t plus 1/2 t, that's t, minus 25 equals 0, which means t is 25. And in this case, it would be pounds because pounds was the unit that was given to us. So there we go. We found the magnitude of the tension, the force on this chain. We just called it the tension vector, T1, instead of the force vector, but it's the same thing. All right, let's kick that up a notch and do it for a pendant, something large, a large chandelier. So we have a large chandelier weighing 500 pounds. It's suspended from the ceiling with the top 4 feet below the ceiling. Workers anchor the 4 cables in the ceiling as shown below. Each cable is rated to 150 pounds. Will the cable support the chandelier? Hello, engineering question. This is the kind of question that's very basic, but it's an engineering question. Okay, so in this particular case, they actually set the origin up here, right? So there's the origin. It's right there. And that's okay. I mean, you can do it different ways. So this particular one is set up so that the origin is that way. Okay, so be it. All right, so we have a force vector pulling down, right? We know that. We know that the force vector due to gravity must exist, and it's pulling this thing down. I think I'm going to do the opposite of what I did in the last one. I'm going to write it up here. So the force vector due to gravity is 0, 0. This is 3-dimensional, so I have x and y, and z is negative 500 pounds. Right? It's pulling it downward. That's why it's negative, because it's going down. Okay, and then I have these other force vectors. Aren't they cute? So we have force vector 1, force vector 2, force vector 3, force vector. It doesn't really matter which one we pick to be what. It doesn't really make any difference. So I chose that one to be force vector 1. This one is force vector 2. This one's force vector 3. I don't quite know why they made the arrows point downward, other than, well, there might be some physics reason. But for us, for the mathematical portion, we don't need it. Okay, so we have our 4 force vectors. And then let's think about each of those force vectors. So force vector 1 is working like this. The magnitude on it is, of course, T. All of them are carrying an equal amount of load because of the way that it's suspended, right? So because they're all at 2, 2, 2, 2, it's all equal, everything all perfect around. So everything will be holding it the same amount. So if you think of the vector, let's just do this for, I'm only going to do this for number 1 so you guys can see it. To make this, it's a little complicated. What you're doing is the terminal minus the initial, right? The terminal point minus the initial point, which would be 0, 2, 0, take away, we're finding it here, take away 0, 0, negative 4. Now the problem with this, oh, and that would be 0 to negative 4, right? No problem. Oh, excuse me, minus a minus 4 is plus 4. Good grief. I can't do basic math anymore. All right, so 0 to 4. Okay, but the problem with that is just whatever length it is, and we need it to be t units long. It can't just be whatever it is. So we have to unitize it. Right? We need to make a unit vector. I was about to draw my u very strangely. My unit vector in the direction of force 1. So that would be 0 to 4 divided by the square root of 0 squared plus 2 squared plus 4 squared. That's 16 and that's 4. So that is 0 to 4 divided by the square root of 20. That turns it into length 1. But I don't want it to be length 1. I want it to be length t. So all of this combines together to lead us to force vector 1 is t times 0, 2 over the square root of 20, 4 over the square root of 20. And yes, that does reduce if you want it to. It doesn't really make any difference to us. But 4 goes into 20 5 times. So this is 2 square root of 5. So that would be t times 0, 1 over the square root of 5, and then 2 over the square root of 5. That works. Right, I'm just kind of making that there. I'm doing that in my head, and then I was canceling some numbers. Okay, so if that's force 1, now keep in mind, look at all the other vectors. They all kind of work the same, right? It's just that the 2 is in a different spot. Sometimes the 2 is in the x direction. Sometimes it's in the y, but it's negative. Sometimes it's in the x, but it's negative, right? So that means that force 2 would be negative 2. It'd be t times, it'd be negative 1 over the square root of 5. 0, 2 over the square root of 5. Right? Because the 2 is the one that's changing position. The rest of them are all the same. So it'll be fine. And then force 3 would be t times, the 2 is in this position, so it'll be 0, negative 1 over the square root of 5, 2 over the square root of 5. Right, because the negative 4 is why that one happens. And then force 4, if I can fit it in here, we'll have a positive 2 again. So that would be t times positive 1 over the square root of 5, 0, 2 over the square root of 5. Right, there are your force vectors, all of them. You have your force due to gravity plus these other 4. Now to make equilibrium, so that this is going to hold, you need to add up all the pieces, right? So force 1 plus force 2 plus force 3 plus force 4 plus force 5 plus the force due to gravity. Here, let me do this in green. Force 1, force 2, force 3, force 4. You need to add them to the force due to gravity, and you have to be able to get the 0 vector, which would be 0, 0, 0, which is the 0 vector. Okay, well, let's look at these for a second. So if we add them all up, if I take force 1, force 2, force 3, force 4, and force gravity, just look at the x components for a second. This x component, this is 0, this is 0, this x component. If you add them together, you're going to have 0, right? So this is going to be a big fat 0 for the x component. For the y components, that's going to be 0 for the gravity one. 1 square root of 5, 0, negative 1 square root of 5, 0. So if I add those two numbers together, I get 0. All right, so the y component is a big fat 0. So now let's look at the force, the z. This is where the rubber meets the road. So we have a negative 500. We have a 2 over the square root of 5, a 2 over the square root of 5, another one, and another one. So we have 1, 2, 3, 4 t times 2 over the square root of 5 minus 500. And that has to be equal to the 0 vector. Okay, so that means that this piece must be equal to 0. So 8 over the square root of 5 times t minus 500 equals 0. I'm just multiplying 4 times 2 there. And then we bring the 500 over. And then we multiply by the reciprocal. And of course we do it to both sides to keep it fair. So t is 500 times the square root of 5 over 8, which we will find with a computer. I just typed it in. So I got 139.75. All right, so 139.75 pounds. Now I'm not circling it because it's not the answer. We have to go back and say each cable was rated to 150 degrees, or excuse me, 150 pounds. Will the cable safely support the chandelier? Yes, right? So yes, the cables will support the chandelier. Because 139.75 is less than 150 pounds. That's the question that was being asked.